How confident are you in answering test questions about projectile motion? In today's video, that's exactly what I'm going to discuss with you. I've selected 4 conceptual questions and 1 problem solving regarding this two-dimensional motion known as projectile motion. So before we start answering the questions, may I invite you to recall, right, or review some important key concepts in analyzing projectile motion. So in the table shown, okay, we say that a projectile motion is composed of two types of motion which are independent to each other. Okay, we have the vertical component of the motion and the horizontal component. All right, the vertical component of the motion is actually one that is uniformly accelerated, and the other component, the one along the horizontal, okay, is a uniform motion. Okay, so these two types of motion are independent. In other words, one does not affect the other. So let's take a look. How do we describe the acceleration of a projectile as far as its vertical motion is concerned? Right. So we say that the acceleration along the vertical, we label that as a sub y, is in fact equal to negative 9.8 meters per second squared, which is always constant. Okay, that's exactly the acceleration due to gravity. Now, the horizontal component of the motion has no acceleration along the x. Okay, our ax or a sub x equals 0. Now, why is this like this? It is because the net force, okay, acting on a projectile along the vertical is just the force of gravity, or also known as the weight of the projectile. Now, for the uh, horizontal component of the motion, there is no net force, right? There is no net force along the horizontal, and that is the reason why its horizontal acceleration is also equal to 0, all right? But you may be wondering how come in a projectile motion, the body seems to continue to move horizontally. Okay, what is the reason why a projectile when launched, okay, continues to move along the horizontal if indeed there is no net force along the horizontal? All right, all right. The very reason why a body is continuously moving in a horizontal motion, okay, is simply because of the effect of inertia in motion. All right, and this is based on Newton's first law of motion. Okay, the first law states that an object that is moving uh, with constant velocity, okay, meaning constant speed in a straight line, is not acted upon by any external net force along the horizontal. Okay, if you are talking about projectile motion, so it is inertia that keeps it going. But take note, inertia is not a kind of force. It's just the tendency of a moving body to continue moving in the absence of an external net force. All right? So, how about the velocity? Okay? What can we say about the vertical component of the velocity? So, it depends if the body or projectile is on its way up. We say that the magnitude of the velocity along the y, okay, is decreasing in magnitude, but it is in fact heading towards the positive direction because we consider upward to mean along the positive y direction. All right. At its highest point of its trajectory, we say that the vertical component of the velocity or the speed must be equal to 0. All right, take note of that. The instantaneous speed or velocity of a projectile along the y. All right, we usually denote that by the symbol by. All right, meaning uh, the vertical component of the velocity when the body reaches the highest point of its trajectory, it is in fact equal to 0. Okay, then what about on its way downward? So, since we consider a downward motion to have a negative direction, all right, but the magnitude of the velocity is in fact increasing, or the body is speeding up, right? For the horizontal component of the velocity, all right, this is very important, okay, to remember. The horizontal component of the velocity is always constant, no matter where the projectile is located, as long as it is still in flight, all right? The horizontal component of its velocity is just the same all throughout the curved path, okay? We normally represent this with the symbol v sub x, and this v of x is always constant. It doesn't change. Okay. A usual, what do you call this? A usual misconception. Okay. Uh, as far as the horizontal motion is concerned, because it is referred to as uniform motion, the word or the phrase uniform motion, in fact, is describing that the horizontal component of the velocity is constant. Constant in magnitude, constant in direction. Right. Now, let's go to the displacement or the distance. Okay. For the vertical component of the motion, we use this formula in determining the change in y, or change in the vertical displacement. Okay. So, looks familiar because this is the kinematics formula that uh, we have been using in our analysis of kinematics. All right, we have here to find the delta y. All right, we just apply the formula b of 0, meaning the initial velocity squared plus 1/2 gt squared. But in using this formula, we always note that we are referring to the vertical component of the velocity. Okay, not the actual velocity of a projectile, but just the vertical component. So there should be a subscript y. Okay, when you're going to use this formula, there should be a subscript y, such as b of o or b of 0 y squared. to emphasize that you are talking about the vertical component of the velocity initial. Okay. Now, there is a formula also that relates the maximum height reached by a projectile, okay, in terms of its initial velocity, okay, v sub 0, or sometimes they call this v sub v naught, meaning the actual. This is the actual initial velocity. This is not just the y component, but this is in fact the actual initial velocity or initial speed. Okay, so the formula is initial speed or initial velocity square multiplied by the square of the sine theta. Okay, sine theta, you first get the sine value of the angle theta, and then you're going to square it before you multiply that to the square of the initial velocity. Okay, then divide by twice the acceleration due to gravity. We don't treat the acceleration due to gravity as a vector. So we normally have a negative sign for the value of g, but in using this formula, okay, we don't consider the negative sign of g. All right, because we are only talking about the maximum height reached. We treat the displacement, the upward displacement, as a scalar quantity. Okay? Now, for the horizontal component of the motion, we only use this simple formula in determining the horizontal distance or displacement, delta x. Okay? It is equal to b sub not x, meaning the initial velocity along the x. Okay, this is the x component, which we earlier described to be always constant. Okay, so if you multiply this by the time of travel or the time of flight, okay, you will be getting the distance traveled along the x. Sometimes they call this the range of the projectile. All right, and speaking about the maximum range, we also have a derived formula. Okay, this is similar to the case of the maximum height. Okay, so to determine the maximum range that is traveled by the projectile, we just get the square of the initial velocity or initial speed, right? Get the square of that, then multiply it with this quantity sine 2 theta divided by g. What is the meaning of sine 2 theta? All right. If you're given the angle of projection, you just multiply that by 2. All right. And then get the sine of that angle. For example, the angle is 30 degrees. You will have to multiply 30 by 2. That makes the angle now equal to 60. And then you get the sine of 60. Okay? So that's different from sine squared theta. Because in here, you first get the sine of the angle, and then you square that value of the sine theta. Whereas here, you multiply the angle first by 2. All right? And then get the sine value of the angle that has been multiplied by 2. Okay? Notice also another difference between the two equations. For the R max, there is no times 2 in the denominator. So just the value of G with no sign in it. Whereas for the H max, you have to multiply the absolute value of G by 2. So these are the important or the key concepts when you're analyzing projectile motion. We shall apply these concepts as we start answering the 4 conceptual questions as well as the problem-solving questions uh, towards the end of this tutorial. Let's take a look at an illustration of how we analyze the motion of a projectile. Okay, so we have here initially at this point O, meaning the origin, the projectile has an initial speed labeled here as v sub 0 or v naught, right? Now, as a velocity initial, it also has an angle theta, initial angle theta, with respect to the x-axis or the horizontal, right? Also, you have here the x and the y components of the initial velocity. It is labeled here as v sub 0x or v naught x directed to the right, while the y component is labeled v sub 0y or v naught y directed upward. All right? So this is initial at the initial position. It's understood that the projectile has already been released, okay, or projected, okay, from whatever source. For example, when you are throwing a ball, okay, the ball is assumed to have been released already from your hand. Okay, so it's no longer in contact with your hand. That's why we said earlier in our summary of concepts, okay, the only force acting on the projectile is the force of gravity in the absence of air resistance, all right, which is normally assumed. The only force acting on a body in projectile motion is the force of gravity, right? So what happens if the projectile reaches this point here? All right. There's the acceleration due to gravity labeled here as g. All right. We said earlier in our discussion of the concepts that the acceleration along the y is always equal to g. All right. And that is always constant, as shown here. Whether the body is on its way up, whether it's already at the maximum height reach, okay, or on its way down, okay, when it reaches that point, which is of the same level as the initial position, or if there's still space to move further down, then we also include that position there. All right, the acceleration due to gravity is still there, constant. Right. Notice how the uh, magnitude of the velocity changes. All right, from the initial position up to this position, okay, we see a decrease in the actual velocity because the vertical component, okay, the vertical component of that velocity is also now decreasing. Okay, from here now, okay, we can say that the vertical component of the velocity is already less than what it has initially. But the x component of the velocity is constant. What it had earlier initially is still the same. Okay, upon reaching this point, the Vx is still the same, doesn't change. But when added, okay, vectorially, the Vx and the Vy, when added vectorially, okay, you will get the resultant velocity, okay, which is the actual velocity tangent to that point here. So, upon reaching the maximum height, what happens to the vertical component of the velocity? All right, it's already equal to 0. The instantaneous velocity along the y is now 0, but the horizontal component of the velocity is still constant. All right? So it's wrong to say that when the body reaches the maximum height, it's wrong to say that the velocity, instantaneous velocity of the projectile is equal to 0. That is a common misconception. Okay? There is still the x component of the velocity, okay, directed to the right, just like what it had all throughout its motion. From the beginning up to the time it reaches the maximum height, the horizontal component of the velocity remains the same. Now, on its way down, remember it continues to move because of inertia until it reaches this point, supposing this point is of the same level as what we have here. All right? We say that the downward component of the velocity Vy, okay, it's now going down, and so therefore the velocity component along the y is now negative. All right, negative downward velocity. Okay, but the horizontal component is still constant. So when added vectorially, we have the actual velocity tangent to that point there. That's represented by the letter v. All right, comparing the magnitude of that velocity at this point to the velocity when the body is still on its way up, we say that the magnitude, okay, is the same. All right, whatever is the angle here, all right, the angle theta that is above the horizontal, okay, is also the same angle when the body is at this point, okay, but the angle now is below the horizontal. That's the only difference. And when the projectile has reached that point, okay, which is of the same level as what it had initially, all right, there's still the acceleration, okay, along the vertical, which is constant. Acceleration is constant, equal to g, but the vertical component of the velocity, which is directed downward, has already increased in magnitude. Whatever the initial magnitude here of the vertical component, that's just equal to what it has at this point. All right, it's only the direction that's opposite. But again, the horizontal component is still there, constant. So when you add vectorially the Vx and the Vy, you again get the resultant velocity, whose magnitude is just equal to the magnitude of its initial velocity at the initial position. Now, if there's still a space, okay, to further move downwards, for example, at this point, all right, then again, we say that the vertical component of the velocity has now increased, okay, in magnitude, but still downward, and the horizontal component is still constant. When adding these two components, again, we have a resultant velocity that is much higher compared to what it had, for example, at this point. Okay, so that's how we analyze uh, the motion of a projectile, okay, at any given position in its trajectory. Also, as far as the horizontal displacement is concerned, all right, which is just dependent on the value of the x component of the velocity, okay? So when the body reaches this point here, we showed earlier that the range or the x, the horizontal component, of the displacement, okay, we call it the range, is just equal to the Vx multiplied by the time it takes for the body to move from here up to here. Okay? Now, if there is still a continuous motion beyond what we have here at this horizontal, all right, horizontal, what do you call this? Horizontal distance. Okay, if there is still uh, an additional motion, then we will be adding whatever horizontal displacement that the projectile will attain, okay, that will be added to what it has from the initial position to that position. Uh, this kind of situation actually is similar to a case when the projectile is launched, for example, from the top of a cliff. All right. So the projectile goes up, reaches its maximum height, but when it returns to the same level, all right, assuming the cliff is very, very high, all right, very, very high, so it's still, the projectile still continues to move further down until it reaches the ground, or the horizontal distance, okay, below the cliff or at the base of the cliff. All right. So that's how we analyze this kind of projectile motion. This is now the first conceptual question. Okay. Um, a baseball is hit upward and travels along a parabolic arc before it strikes the ground. Which one of the following statements is necessarily true? Ignore air resistance. Okay, so we're looking for this statement that is necessarily true, meaning it is always true, okay, no matter what. Is it letter A? The acceleration of the ball decreases as the ball moves upward. Or is it letter B? The velocity of the ball is zero when the ball is at the highest point in the arc. The arc meaning the trajectory. Letter C. The acceleration of the ball is zero when the ball is at the highest point in the arc. Or is it letter D? The x component of the velocity of the ball is the same throughout the ball's flight. So which among these statements is necessarily correct or true? All right, what is your answer? Correct answer is letter D. Why is this so? All right, let's review each statement again. Why is statement A considered incorrect? The acceleration of the ball decreases as the ball moves upward, so the word decreases makes the statement incorrect. As we said earlier in our analysis or review of the concepts, the acceleration of the ball, all right, as the ball moves upward, so it's referring to the upward acceleration, all right? It's referring uh, to the magnitude of the acceleration as the ball moves upward. Why is this not an acceptable answer? Because of the word decreases. As we all know, the acceleration of the projectile or of the ball here, okay, along the way, the acceleration is constant. Doesn't decrease, it doesn't increase. In fact, it is equal to negative 9.8 meters per second squared. All right, as far as the horizontal component is concerned, there is no acceleration. Along the x, it is equal to 0. So overall, we say that the acceleration of the ball, okay, on its way up is not decreasing. How about letter B? Why is it incorrect? The velocity of the ball is 0 when the ball is at the highest point in the arc. All right? This was mentioned earlier that upon reaching the maximum height, all right, we say that only the vertical component of the velocity becomes 0. All right? But not the horizontal component of the velocity. So in short, the actual velocity of the ball upon reaching the maximum height is not 0. All right? Letter C. Why is this incorrect? The acceleration of the ball is 0 when the ball is at the highest point in the arc. Okay, so again, this is a misconception. Right? The acceleration of the ball is not 0. Why? Because there is still the pull of gravity acting on the ball. All right? That is the very reason why it continues to accelerate constantly, okay, even if we are talking about the maximum height. Okay, there's no acceleration horizontally. Okay, there's no horizontal component of acceleration, but the fact remains, the body is still acted upon by the force of gravity. The net force, in short, is not 0. The net force at that instant is still downward, equal to whatever the weight of the ball is. Okay? So, it follows that the acceleration of the ball cannot be 0. It is in fact equal to negative 9.8 meters per second squared. So the best answer really is option letter D. The x component of the velocity of the ball is the same throughout the ball's flight. Question number 2. 4 marbles are projected or released simultaneously from the same point or elevation. Okay, you have here the diagram. Marble A is released horizontally. Marble B at an angle theta equals 45 degrees above the horizontal. So there's marble B. Marble C also released at the same angle theta but below the horizontal. Okay, below the horizontal. So this is also 45 degrees. That's 45 degrees there. And marble D is simply dropped straight down. Okay. And we say further that marbles A, B, and C all have the same initial speed. Okay. And marble D has 0 initial speed. So among the 4 marbles, it's only marble D that has 0 initial speed. All right. It is simply dropped downwards. Okay. It is not what you call projected horizontally. Okay, it has no horizontal component. It's like an ordinary free-falling body. Okay, that is marble D. All right. So how do we analyze this? The question is still in the next slide, but at this point, because you still have here the drawing, all right. When you say the same what's that? The same initial speed, all right? The same initial speed, all of them have the same initial speed. For example, if the initial speed of A is, say for example, 10 meters per second, okay? That is also the speed for marble B, 10 meters per second. Similarly for marble C, that's also 10 meters per second, all right? The only difference is that their direction, initial directions are different, all right? So the key word used here is the word speed, the same initial speed. We cannot say that they have the same initial velocity. All right, that's different. The fact that all these marbles, marbles A, B, and C, all right, are projected at different angles, all right, from the horizontal, even if the magnitude of their velocities are the same, but velocities per se, okay, of these three marbles are not the same. The best term to use is initial speed. All right, let's now look at the question. All right, so the actual question number 2, okay, which marble or marbles will have the greatest speed just before hitting the floor? Okay, in the drawing, there's the floor, okay, and here's the elevation, okay, from where the marbles were released, okay. We are going to ignore air resistance, and we are looking for one or more answers. There could be just one answer, there could be two, three, or four. All right? So let's start analyzing this uh, question. Okay, analyzing the motion of each of the marbles before I reveal to you the answer or the correct answer. All right. So how do we start? We say that the speed of marble B, okay, the speed of marble B as it goes up and then comes back to the same level, all right? Uh, the speed of marble B when it comes back to the same level from where it was launched, that's labeled as V sub B2, okay? V sub B2 meaning its second position, considering that the initial here is V1, all right, BB1. When it comes back, that's what I mean by B sub B2. The velocity or the speed, I should say, the speed of marble B when it reaches, all right, that point with the same level of the initial position. So it says here that is equal to the speed of marble C, okay, at its initial position. All right. Why is this analysis correct? Because it was specified that marble B, when launched upward at an angle of 45 degrees, all right, 45 degrees, when it goes up, then reaches the maximum and then comes back, it actually uh, assumes the same situation as marble C, okay, whose angle from or below the horizontal is also equal to 45 degrees. So that is how we compare uh, the motion of marble B with marble C. Hence, this means that okay, the velocity of marble B upon reaching that point there, all right, with of the same level as the initial position, it will acquire a velocity, okay, equal to that of marble C. Okay, so that's it. So if we are going to continue analyzing what's going to happen, okay, to these two marbles, marble B and marble C, when they reach, okay, when they reach the floor, right? Since exactly what is happening to marble C, okay, at the start will also be the case of marble B. It's just that if they are released at the same time, all right, marble C, of course, will reach the floor, okay, much earlier than marble B. But upon reaching the floor, okay, these two marbles will be having the same value or amount of velocity. Okay, it's just that marble C will reach the floor first compared to marble B, but their final velocities, okay, upon reaching the floor will just be the same. And that is what is meant by this second equation. The final velocity of marble B, labeled here as V sub B3, is just equal to the final velocity of marble C, also upon reaching the floor, B sub C2. All right? Now, what about the two other marbles, marble A and marble D? For marble A, the fact that it has no vertical component of the velocity, okay, the y initial for marble A is understood to be equal to 0. All right? It has no vertical downward downward vertical component of the velocity of marble A is equal to 0. And when we compare, okay, the fate of marble A and marble C, definitely marble C again, okay, will acquire a much greater uh, vertical component of its final velocity just before hitting the ground or the floor, isn't it? Because it has an initial vertical component, okay, of its velocity, and surely upon reaching the floor, it will have a higher vertical component of the velocity compared to marble A. Okay? And similarly, marble D, which has no vertical initial component, okay, will also have the same vertical or final vertical component of the velocity with that of marble A. See? So, in other words, among our choices, okay, which of these options, okay, will be considered correct? We are expecting one or more answers. So, the correct answer or answers, right? Here is the analysis, by the way, before we reveal the answer. No? This is the analysis in comparing the velocity of marble D with marble A. We say that initially, they don't have the y component of velocity, so both have 0, okay, initial y component of the velocity. All right? But what happens, okay, what happens upon reaching the floor? So there you are. V dy means the final velocity along the y, all right, of marble D being equal to that of marble A upon reaching uh, the floor. But each of them will have a lower or a less final velocity compared to marble B or marble C, right? So that less than, that sign of less than, okay, meaning the final velocity for both marble B and marble C, okay, are greater than those of marble D and marble A. Therefore, our correct answers are marble B as well as marble C. Okay? Okay. There's an additional question regarding the motion of marbles A, B, and C, or A, B, C, and D. Okay, and this is we we want to know which among the four marbles will have the greatest horizontal distance. Okay, horizontal distance meaning the range or the distance from the foot of this elevation, all right, whatever it is, table or whatever, how far it is from the point of uh, where the each marble strikes. Okay, so we expect one or more answers again. Uh, Among the three marbles, obviously, marble D will no longer be moving horizontally because it has no x component of its motion. All right, so marble D is out of the choices already. So it's only marbles A, B, and C that we're going to compare. Okay, so it's quite logical, all right, to say that marble B will take the longest time to travel, okay, from its initial position until it reaches the floor, okay, for the mere fact that it still goes up, all right, reaches maximum height before it comes down and continues until it reaches the floor. That's not the case for marble A because marble A doesn't go up anymore. It immediately moves down in a curved path. So in that sense, we can say that it takes shorter time for marble A to reach the floor. Okay? And for marble C, since marble C has already an initial downward velocity, all right, unlike marble A, which has no initial downward velocity component, marble C already has a non-zero downward initial velocity, all right, and that helps marble C to reach the floor much earlier compared to marble A, isn't it? Uh, Earlier, it was mentioned earlier that marble B, upon reaching this point at level with the initial position, will sort of become what is happening to marble C. In other words, the velocity of marble B upon reaching this level, all right, will be the same as that of marble C. They both have the same angle with respect to the horizontal, and the downward velocity of marble B, the vertical component, is equal to that of marble C. So we say that both marbles B and C will be reaching the floor with the same final velocity. Okay, that was our answer in the previous question. Uh, so it is logical again to say that marble C, okay, will also acquire a much smaller horizontal distance compared to either marble B or marble A. And this is also backed up by our concept that the horizontal distance or displacement delta x depends on uh, the horizontal component or Vx as well as the time of flight. All right. So in terms of the time t, okay, it's uh, it's obvious that marble B will be having the longest time of travel, okay, and the least time is marble C. Marble A is just between marble B and marble C. That is it. We consider the delta x uh, in terms of the time of travel. Okay, that's pretty obvious. But in terms of Vx, since it was mentioned that all these marbles have the same initial speed. For example, if the initial speed of marble B is 10 meters per second, that's also the initial speed of marble A and also of marble C. Okay? But what happens to the horizontal component of the velocity of marble B? It will no longer be equal to 10 meters per second, right? Because part of the 10 meter per second that we assume will go to the vertical component. Okay? In short, in terms of Vx, the Vx of B, okay, will not be as large compared to that of marble A. Okay? All the velocity of marble A initially, okay, uh, goes into Vx because it has no initial Vy. All right. So from on that premise, we can say that based on the x component of velocity, a a would have a greater range compared to b. But that's not really the case, okay? Because as we have mentioned, it is the time of flight of marble B, okay, which is very much longer compared to that of marble A. That will explain why the horizontal distance traveled by B, okay, should be much longer than that of A. All right. So that is how we explain uh, their what do you call this? Their horizontal distance or the range that they will be getting upon reaching the floor. Now, if you're going to arrange, okay, their horizontal distance traveled from the bottom of this, for example, this is a table, no? So from the bottom of the table to the point where they strike on the floor, this is how we arrange, okay, the corresponding ranges. It's greatest for marble B, okay, compared to marble A, and of course compared to marble C, okay. Marble D, already said that has no horizontal distance because it's all vertical. All right, its motion is all vertical. So in other words, what we did here is to answer the question uh, based only on logical reasoning, all right? But part of it, of course, is to apply the concept of delta x being equal to Vx times t, all right? So combined logic and this concept, okay, I hope you are convinced of our comparison for the for the horizontal distance traveled by each marble. Therefore, our answer is letter B. All right, this is our last conceptual question. Okay, which statement below is necessarily true or correct when the equation R max equals bi squared sine 2 theta over g is applied? Okay, so this was already presented earlier. The R max is the horizontal distance acquired by a projectile, all right, when the projectile is launched at a certain angle above the x-axis or above the horizontal labeled theta, okay. V initial is the actual initial velocity, then you square it. We are not talking about the x component, the velocity, but this is the actual, okay, the actual uh, velocity that makes an angle theta above the horizontal. So in using this Rmax formula, okay, uh, which among the statements A, B, C, D is necessarily true? All right. So we note here that the angle theta is from the positive x-axis. In short, we're talking about a kind of projectile that is launched diagonally upward. All right. This doesn't apply. This formula doesn't apply to cases when um, a projectile is just launched horizontally, all right, or diagonally but downward. If the angle is below the x-axis, okay, that's not. Uh, that's not a situation where we can apply this formula. So, looking at each of the options, letter A, two projectiles launched at angles 30 degrees and 60 degrees will have the same range. Letter B, two projectiles with equal initial velocity, all right, launch at angles 15 degrees and 75 degrees will have the same range. Then letter C, two projectiles with equal initial speed launch at angles 25 degrees and 65 degrees will have the same range. And option D, as the angle of launch of a projectile increases from 0 degree to 90 degrees, the range also increases. Alright, so these statements have something to do with how you understand the meaning of this equation, R max. Alright, so earlier, while discussing the concepts, I already mentioned to you that the meaning of sine 2 theta, alright, is that before you get the sine value of the angle theta, you first have to multiply the angle by 2, right? That is what we mean by sine 2 theta. Then divide it by g. Alright, so assuming that the value of V1 is the same, constant, and the only thing that differs between two projectiles is the angle of launch. Alright, the angle of launch, for example, 30 degrees. Okay, case 1 is the angle of release or the angle of projection is 30 degrees. And for another projectile with the same initial speed, the angle of projection, for example, is 60. Alright, the first projectile has an angle of projection of 30, the second one has an angle of 60. So what happens? You can check, all right? Since we let Vi equals a constant, so we just look at what's going to happen to the R or to the horizontal displacement, no? If those angles are considered. What is the sign of, for example, if the angle theta is 30, that means that's 60, all right? What is the sine value of 60 degrees? All right, you can check that in your calculator. And what if the angle is, or the theta is doubled? Make it 60 degrees. Since we multiply by 2, that becomes 120, all right? And what's the sine value of 120 degrees? You will find out, you check with your calculator, that the sine values of 120 and the sine value of 60 degrees are just equal or the same. In short, I'm sure you know this already, that if the two angles of a projection are what we call complementary angle. Complementary meaning if you add the two angles, their sum must be equal to 90 degrees. All right? So 30, the complementary angle of 30 degrees is of course 60 degrees. All right? That's in letter A. The two angles mentioned are 30 degrees and 60 degrees. All right? So it says two projectiles launched at angles 30 and 60 will have the same range. All right? That's the way it is stated. No mention about the initial speed. It just mentioned the angles 30 and 60. All right? You know what the best answer is? All right? The best answer here is actually option letter C. All right. Now you start to wonder why. Okay? You will notice that statement B and statement C are just quite similar. All right? What's the difference? It is the choice of the word. Okay? Here we talk about, in letter B, we talk about initial velocity. While in letter C, we talk about initial speed. So what's the difference? Why is letter C a better answer compared to letter B? All right? When we say the two projectiles are of the same initial velocity, okay, it should mean that the magnitude of the velocity of the two projectiles must be the same, all right? And their directions must also be the same. But how can that be possible when it states that the angles are different, all right? So there is something contradicting here, okay? The use of the word velocity makes the statement questionable, all right? We cannot have the same initial velocity while having different angles of projection, okay? Whereas in letter C, the use of the word initial speed, we're only referring to the magnitude of the initial velocity, all right? So it's a better answer because we are safe. If you use the word initial speed, uh, their directions may be different. And in fact, the first one, all right, the first projectile has an angle of 25 degrees, all right, from the horizontal, and the other one, 65 degrees. But their initial speed, okay, are the same. It's just that the angle of projections are different. And 25 as well as 65 are complementary angles. So when substituted in the formula, okay, the sine value, for example, of twice the theta 25, that means 50. The sine of 50 degrees is just equal to the sine of 130 degrees. 65 times 2 is 130, all right? So having the same speed, that means their Rmax will be the same. So in short, letter C, okay, is necessarily true or correct, but not letter A. Two projectiles launched at angles 30 degrees and 60 degrees will have the same range. What is lacking here is to specify that their speeds, all right, must be the same. It doesn't say here that the speeds, all right, for these two projectiles are equal. So in short, this is not necessarily true, all right? They may be complementary. The 30 and the 60-degree angles are complementary, but no mention whatsoever about their initial speed. So it's not necessarily correct, all right? So we already explained why letter B is also incorrect. And wait. Letter D, option letter D says, as the angle of launch of a projectile increases from 0 to 90 degrees, the range also increases. That's not really accurate because, again, using this formula, all right, what do you think is the maximum angle? At what maximum angle will a projectile acquire the maximum range or the greatest value of range? At what angle? It is at angle 45 degrees, all right, where the sine value of twice the angle, which is 90 degrees, is already the maximum possible value for the sine, which is equal to 1. All right? But starting from 0 angle or 0 degree angle, okay, from 0 degree to 45 degrees, but not 45, okay? Not inclusive, but exclusive, okay? The range should be increasing, all right? And then beyond 45 degrees, all right, up to 90, okay, not in 90 not included. Again, it's exclusive. What happens to the range? The range in fact decreases. As the angle approaches 90 degrees, there will be no more range, isn't it? So that statement in option D is not exactly true. All right. If you are asked to modify this statement, what you should say must be, as the angle of launch of a projectile increases from 0 to 45, then the range increases. But if the angle is increased from 45 up to 90, the range decreases. That is how you should modify this statement. But right now, it is not necessarily true. So the best answer, therefore, is letter C. All right. We are now on the last question, which is not a multiple choice question, but it's an open-ended problem-solving question. So we have a rifle, all right? A bullet is fired at an angle of 30 degrees below the horizontal with an initial velocity of 800 meters per second from the top of a cliff, all right? So here's our, what do you call this, sketch of that situation. Supposing this the top of the cliff, and a gun or rifle is aimed, okay, in this direction, okay, making an angle of 30 degrees below the horizontal or the top of the what do you call this, that top of the cliff, okay. So from that what do you call this, dash line, right, from the dash line, the angle below it is what we mean by 30 degrees, all right. And the magnitude of the initial velocity of the bullet is 800 meters per second. All right. So we are tasked to determine the height of the cliff. All right. Labeled here as capital H. The distance or horizontal distance from the bottom of the cliff, all right, up to the point where the bullet hits the ground, okay, is given. The range is given as 141 meters. All right. So how do we answer this question? Notice that nothing is mentioned about the velocity upon hitting the ground. Okay, although we know the initial velocity, which is 800 meters per second, but there's no mention about the final velocity. All right. So what is the equation and what is the quantity that we have to first calculate? All right. So we will see. Um, the first thing that we're going to calculate is the x and the y components of the initial velocity. All right. This is how it is done. We get the x component by simply using the formula v1x equals cosine 30 degrees multiplied by the initial velocity of 800 meters per second. Right? Why cosine? Because the x component for this initial velocity is the adjacent. All right. We can imagine a right triangle here. Okay, the right triangle is such that the given initial velocity, okay, constitute the hypotenuse. All right, and the x component of that velocity becomes the adjacent side of the triangle. All right. So therefore, the trigonometric function that is suitable in finding the x component would be cosine. Cosine of the angle 30 degrees times 800 meters per second. Okay, using your calculator, we get that value of b1x, 693 meters per second. And how about the y component? All right, the y component um, is simply determined by using sine of the angle 30 degrees and multiplied by the same value of the initial speed. All right, because the y component is actually the opposite side. If you imagine again that uh, triangle, okay, it is the side opposite to the angle 30 degrees. So when we are getting the ratio of the opposite side to that of the hypotenuse, it must be sine. That's the meaning of sine of the angle 30 degrees. All right, so again, doing your, using your calculator, all right, we will get the value for B1Y, which is 400 meter per second. But we include the minus sign because this Y component is directed downward. All right, so that negative sign of our uh, B1Y must be emphasized because we are treating this quantity as a vector quantity. Okay, so from there, how do we continue with our computation? Now that we know the Y component of the initial velocity, okay, we can now determine the time of flight, okay, the time t. How long it will take for the bullet to hit the ground, okay? That is what we mean by the time of flight. And that can easily be determined because we are already given the horizontal displacement or the range, which is 141 meters. Okay, the relationship between the range and the Vx, all right, is such that, okay, we earlier represented this. The range is just equal to Vx multiplied by the time t. And transposing that equation to solve for the time t, we have range divided by Vx. All right, so we just divide 141 meters because that's the value of the range by the x component, all right, of the velocity, 693 meters per second. That's the one there, all right? And what we get is a value of the time of flight equals 0.203 second, okay? We, what do you call this? We follow that the rules of significant figures where our answer has to be in 3 significant digits. So that's the time of flight, okay? That will now help us determine the variable height, all right? Or the displacement, the downward displacement of the bullet, okay? Sometimes also referred to as the delta y. But we just have it directly in our equation to find the height h, all right? Although we will be treating it also as a vector, but our symbol is already the symbol for the height h. All right, but we will be treating the downward velocity b1y as a vector quantity as well as the acceleration due to gravity, which is negative 9.8 meter per second squared. We already know the time t, so upon what you call this, upon substitution, okay, the b1y or the downward vertical component of the velocity has been determined earlier. That is negative 400 meter per second. All right, so I will not include the unit here anymore for lack of space. All right, so negative 400, that will be multiplied by the time of 0.203 seconds, and then add half of the value of g, negative 9.8, and then the square of the time, 0.203 square. All right, what we will get when we multiply negative 400 times 0.203, we will get negative 81.2. All right, and then for this 1 half, negative 9.8, multiplied by the square of 0.203, what we will get is negative 0.202. All right, so the two terms or the two numbers are both negative. So we simply add them. That gives us 81.4 meter. All right, displacement is downward or below the top of the cliff, which is our reference. All right, so we consider the displacement below the top of the cliff to be negative, equals 81.4 meters. But since what we are looking for is a scalar quantity, the height, of the cliff, we just remove the minus sign and conclude that the height of the cliff is therefore equal to 81 meters. So that's about all. Okay. I hope you understood how the concept of what do you call this? How we apply the concept of kinematics. Okay. The formula for kinematics in analyzing uh, projectile motion. Okay.